Hi, my name is Kietzmann and I will present our paper, Delay-Tolerant ICN and its application to LoRa. This is joint work with José, Dirk, Thomas and Matthias. This is what we call a regular ICN network in this talk. It consists of networked ICN nodes with caches that are typically connected with wired links that expose latencies at the order of tens of milliseconds. But how do we connect the edge to these networks, which might introduce much longer delays? In this talk, we start from the observation that regular networks and edge networks have a different understanding of round-trip times, which affects the timing behavior and stack configuration of nodes. In our case, we consider a LoRa-based constrained IoT network at the edge, which introduces delays 3 orders of magnitude above those of a wired network. First of all, what is LoRa? LoRa is a wireless long-range technology that transmits data over multiple kilometers with little energy requirements, at the order of millijoules. Thereby, the throughput is heavily limited at the order of bits per second. In more detail, LoRa defines a chirp-spread spectrum modulation, which makes it robust against interference, multipath fading, Doppler, etc. These properties make it an attractive technology for the constrained IoT, where nodes are battery operated and send sensor data sporadically. LoRaWAN is probably the most popular communication system for LoRa devices and defines a vertically integrated network architecture, mainly to upload the IoT data to a server-based infrastructure. At the ICN Conference 2020, I have presented our poster that raised the question whether LoRaWAN is an option for ICN. The short answer is no. In a nutshell, the unreliable uplink communication in LoRaWAN leads to wireless interference, and more severely, centralization around a network server complicates data sharing. To overcome the LoRaWAN limitations, we have proposed and simulated a system redesign in our previous paper. It consists of 2 components. First, an information-centric network layer. We think that this paradigm has many built-in features that assist in dealing with the challenging LoRa domain. Most prominently, built-in caches reduce wireless link utilization, which facilitates node sleep. And second, a new MAC layer. The 802.15.4 DSME MAC handles LoRa-based media access reliably and enables low power consumption. But the round-trip times of 20 to 120 seconds that we found in our simulation setup still challenge practical ICN forwarders, and this is the starting point for our present paper. Here, we aim for a delay-tolerant integration of LoRa edge networks with very long and vastly different round-trip times into a regular and fast wired ICN network. To achieve this, we provide an OS-level implementation of the DSME MAC on top of the LoRa PHY into the IoT operating system RIOT. We introduce new application-agnostic gateway behavior at the edge. These gateways act as layer 3 routers and include ICN caches instead of just bridging to a network server like in LoRaWAN. Additionally, we leverage 2 recently proposed ICN extensions in our design, namely RISE and Reflexive forwarding. And finally, we provide an experimental analysis executed on common IoT hardware. We provide a comparative evaluation of basic NDN-style ICN, we call it vanilla ICN, and the aforementioned extensions. Now, in the remainder of this presentation, I will first dive a bit deeper into the problem space, the role of interests and timeout values, as well as common interest retransmission procedures. Afterwards, I will give insights into our gateway design and the protocol extensions that we evaluate to compare to vanilla ICN. I will show implementation details at our measurement deployment, which we use for the evaluation. And finally, we'll conclude and express future research directions. So what are the problems when connecting these networks in a delay-tolerant manner? In the remainder of this presentation, I will focus on NDN-style ICN. Interests are central in the receiver-driven control loop of ICN. They trigger data transmission in the first place, which determines the throughput. In the second place, interests trigger retransmissions in case no corresponding data has been received within a certain time. This retransmission procedure is unspecified though. Pending interests are temporary forwarder state and implement the symmetric forwarding property in ICN. This is to record the downstream phase that corresponding data should be forwarded on. A secondary function of PIDs is to enable interest aggregation, a feature that prevents multiple interests for the same data object to be forwarded on the same path. Interest aggregation practically means suppression for all but the first interest that have been forwarded in a certain time, the interest lifetime. When considering producers at the edge with untypical round-trip times, it seems straightforward that consumer applications provide certain knowledge about the time domain and trigger an interest retransmission at reasonably long intervals. This requires PID state to expire timely, otherwise an interest retransmission would always be suppressed by on-port forwarders. But short-lived PID state conflicts with long and varying producer delays introduced by the edge network. Data that faces the forwarder without pending interest will simply be rejected. So one could argue that the interest lifetime needs to be shorter than the retransmission timer. To cater to delay-prone networks, one could increase both values, the retransmission interval and lifetime. They would need to be adjusted for the end-to-end round-trip time. NDN interest packets provide an optional lifetime field that allows the consumer to request more suitable interest lifetime durations. The default value is 4 seconds, which clearly is insufficient for our use case. While technically this seems like a solution, we argue that this is not likely to work well in real-world deployments. First, high-speed forwarders are not likely to honor non-standard interest lifetime values. Second, in DTN scenarios, producer delays and thus consumer-defined interest lifetime values could be significantly higher than the 4 seconds default. A core router might just object to spend more memory resources storing many interests for a very long time. Third, the round-trip time may change unpredictably, so the interest lifetime and consumer interest expiration time would have to be adapted constantly, which introduces inefficiency. And besides that, guessing suitable values is challenging in general. In practice, there are alternative retransmission techniques that we have considered. In-network retransmissions, like in CCN Lite, allow for long-lived pit state on forwarders without suffering from interest aggregation, since each forwarder triggers retransmissions autonomously. Now the problem with this approach is that each on-path node needs to guess suitable timeout values, instead of just the consumer application. Retransmission suppression, as implemented in NFD, suppresses same-name interests within an interval, which allows forwarding of interest retransmissions even in the presence of a matching pit entry. The suppression interval still relies on the estimation of the round-trip time. The main purpose of this approach is prevention of DDoS by interest flooding, so fast sending rates. Dealing with long and vastly different round-trip times remains unsolved. To summarize, guessing suitable timeout values for vastly different round-trip times is challenging. Furthermore, we cannot expect high-speed forwarders in the Internet to honor non-standard and untypically long interest lifetime values. Instead, we argue for dealing with varying and dramatically higher round-trip times explicitly without interfering with the NDN interest lifetime. This is why we included extended ICN protocol mechanisms to relieve forwarders from domain-specific knowledge. In the following, I will introduce our LoRa gateway behavior and 2 delay-tolerant ICN protocol mechanisms. A gateway serves one wireless LoRa network and acts as an application-agnostic caching forwarder that connects a narrowband LoRa network to the Internet. It follows regular ICN behavior in the upstream direction. In the downstream direction, it leverages knowledge about the properties of the wireless last hop and adjusts timeout values accordingly. We have added a node registration feature that takes place after a LoRa node joined the network. A node registers an individual name prefix at the gateway, which acts as a node custodian. LoRa nodes can only serve content under that name prefix. Data provisioning by IoT nodes commonly happens sporadically. Our gateway accepts unsolicited ICN data messages from registered nodes and acts as a LoRa data cache. Content objects are stored in the gateway content store and it responds to interest messages from the Internet. This approach relieves the challenged wireless domain and minimizes the energy consumption on battery-driven LoRa nodes. Furthermore, the slot-based DSME MAC naturally assists prevention of DDoS by unsolicited data messages. A malicious node can simply be muted by the gateway. We include 2 delay-tolerant ICN protocols in our work. The first one is consumer-initiated. We call it delay-tolerant data retrieval. Thereby, an Internet consumer can request content from LoRa nodes. We leverage the concept of remote method invocation for ICN, namely RISE, that supports longer data retrieval times. Upon reception of a so-called RISE request initiation interest, the gateway forwards the interest to the registered LoRa node. A so-called thunk response data packet contains an indication of the estimated waiting time, leveraging linked knowledge. The estimated data arrival time enables the consumer application to set an appropriate retry timer without the need for specific producer knowledge. After repeated interest, the data item is likely served from the gateway cache. The second protocol is producer-initiated. We call it reflexive push. Registered LoRa nodes place content in the gateway cache using the aforementioned data provisioning method. We leverage the phoning home use case of the reflexive forwarding extension that has been proposed to the ICN for standardization. It defines 2 nested interest data exchanges. Content placement on the gateway triggers forwarding the data name to a node on the Internet. The consumer returns a reflexive interest to retrieve the content object from the gateway, as usual. And finally, an optional data ACK terminates the initial interest. In our evaluations, we compare these 2 protocols to vanilla ICN. Thereby, we apply 3 different configurations. The first one is our baseline scenario with common parameter settings. Interests indicate a lifetime of 4 seconds and retransmissions happen after 1 second, reflecting the initial round-trip estimation of TCP. In the second case, a consumer that is aware of the long domain indicates an interest lifetime of 60 seconds and sends retransmissions after 15 seconds. High-speed forwarders, however, do not adopt this long interest lifetime. The third case uses the same parameters as Vanilla 2, but this time forwarders do honor the long interest lifetime. In all three scenarios, we will also compare the case for consumer retransmissions and in-network retransmissions. But first, let's have a look at our implementation and deployment details that we have utilized for the evaluation. We deploy the long-range sensor application on common low-power IoT hardware. In more detail, the NRF microcontroller consists of an ARM Cortex-M4 processor and provides 256 KB of RAM, 1 MB of flash and runs at 64 MHz. The LoRa radio is an external Semtech SX1276. Our sensor node is operated by RIOT and our network stack, which is visualized on the slide. On top of LoRa PHY, the DSME LoRa adaptation layer and OpenDSME and Open Access MAC implementation handle media access and operate the sensor node as a reduced function device, which synchronizes to the DSME slot frame structure indicated by a coordinator. ICN-DSME contains a simple mapping of ICN onto DSME. And finally, on top of the RIOT network interface, we use CCN Lite as a network stack and integrate protocol extensions in there. To reduce implementation overhead, we deploy our gateway on the same hardware as the sensor application. In practice, however, these gateways are not constrained in memory or energy. Our gateway acts as a coordinator for wireless nodes, and it operates a second interface, an Ethernet-based interface that connects to a common Linux-based workstation that bridges to a virtual tub bridge. The fast internet is emulated by RIOT native instances, which allows to execute the same code in a Linux process. We emulate two internet nodes in Mininet, one forwarder and a consumer. Both links expose a latency of 20 milliseconds and we vary the link loss between 0 and 5%. Now that I have introduced our measurement setup, let's look at the evaluation of the system. In our measurement application, we use unique content names prefixed with a node ID and incremental counters. Data contains either a random integer value, an ACK, NACK or wait instruction. Every content item is requested or indicated once with an average interval of 1 minute. We evaluate the completion time of successful transactions. These values are mainly affected by superframe structures of DSME, which dictate the maximum latency of approximately 30 seconds in this configuration. Data losses result in infinite completion times, so the end value of each graph inherently reflects its success ratio. We first look at the baseline case, Vanilla 1. Less than 20% of requests are successful and finish within the default PID timeout of 4 seconds. This is the case for interests that luckily arrive at the gateway shortly before the transmission slot of the MAC occurs. Consumer versus in-network retransmissions and link loss show a negligible effect because the prevalent obstacle here is rejection of data. In a nutshell, expired PID state prevents long round-trip times. Futile retransmissions at an inappropriate timescale introduce overheads without improving reliability. Vanilla 2 is the case for a delay-aware consumer. Steps at 15 seconds indicate the retransmission interval of the consumer. As indicated earlier, this requires on-path PID state to expire fast, avoiding interest suppression. All transactions finish in less than 45 seconds, regardless of link loss. In short, application-aware consumers can recover losses, but their performance directly depends on the arbitrary poll interval that we have set to 15 seconds in our case. So this approach is still highly susceptible to varying delays. In Vanilla 3, forwarders do adopt a long interest lifetime to set their PID timer. Cases without link loss require 32 seconds at max to retrieve all content, which directly reflects the delay distribution of the MAC. The long PID state on both consumer and forwarder allow data forwarding whenever it's ready, but the case with link loss demonstrates the drawback of this approach. Long-lived PID state on the forwarder prevents effective loss recovery by consumer retransmissions and drops the delivery rate to 80%. In-network retransmissions recover some losses and results in 94% delivery. Now the problem with this approach is that we cannot expect forwarders to adopt arbitrary PID timeout values. Long PID state prevents consumer-based interest retransmissions and is unreliable in lossy environments. In-network retransmissions improve the situation but require forwarder knowledge of the latencies upfront, a requirement that we want to exclude. In the delay-tolerant retrieval case, requests finish in almost exactly 32 seconds, which is the returned wait time of the gateway after the first request of a content item. With losses in place, two effects are notable. First, 5% of the requests finish in less than 3 seconds. Here, a loss of the first data packet, which contains a wait instruction, has triggered an in-network retransmission that could already be satisfied by the gateway. And second, 8% of the requests are not satisfied at all, which is an implementation side effect. More details can be found in our paper. Consumer-initiated delay-tolerant retrieval overcomes requirements for long pit state and stops blind polling. It further renders consumer or forwarder round-trip time estimation as unnecessary and leaves this to the link-away gateway. With the producer-initiated reflexive push mechanism, transactions finish with 100% success, and the completion times reflect the delay distribution of the MAC, similarly to Vanilla 3. The additional round-trip time of a nested double interest data flow has a negligible overhead when directed towards the fast network. Losses are smoothly recovered by in-network retransmissions at minimal time overhead. Contrasting Vanilla 3, this approach works with arbitrary producer delays and forgoes the need to adopt long interest lifetime values on internet nodes. Summarizing, the reverse transaction flow in reflexive push reflects IoT data generation most naturally. This protocol facilitates reliable and timely transactions and operates most efficiently, providing the best energy-saving capabilities among all alternatives. Evaluations of the communication overhead of these protocols, as well as the system utilization, can be found in our paper. These results back up our findings presented before. Now let's come to the conclusion of this presentation. In this work, we have observed that interconnecting networks with vastly different round-trip times is challenging. We found that ICN has the unique potential to enable robust communication to LoRa nodes in challenged edge networks without requiring application layer relays. We have contributed a complete OS-level implementation of ICN DSME LoRa and 2 ICN-style extensions together with a reproducible evaluation environment. Our results show that the 2 protocol mechanisms for Internet consumer-initiated and LoRa producer-initiated communication exhibit high reliability. Compared to Vanilla ICN, they enable targeted completion time and overcome polling. ICN DSME LoRa provides low power consumption and enables IoT node lifetimes of over 1 year when operated from an AA battery. In future work, we will integrate an estimator model in the gateway. The gateway can leverage link knowledge to reduce the round-trip time in our delay-tolerant retrieval case without application awareness. We will explore security aspects, which will include the bootstrapping of LoRa nodes and gateways, a secure registration process which requires trust to the gateway, and authentication of a LoRa node before the gateway acts on its behalf. We will evaluate more complex topologies, including multi-gateway scenarios, as well as node-to-node scenarios. And finally, we will investigate additional use cases like remote method invocation and firmware updates on IoT nodes. Thanks for your attention. We support reproducible research. Our code is available on GitHub.